Hello, and welcome to 6.5, the average value of a function. In this chapter, we are looking at applications of the integral. And in this particular section, we are looking at how the definite integral gives us the average value of a function. So if you think of the average or mean of a data set, of a set of values or numbers, you know that you sum the numbers, then you divide by the number of elements in the set. So that's the mean. And that makes sense if you have a discrete, discrete data, which means you have distinct values. So if you think of the integers, you have 1, 2, 3, 4. There are no integers between 1 and 2. There are no integers between 2 and 3, etc. They're discrete. But if you think of the real number line or a continuous function, those values are continuous. You can always find another value between two particular values in the set. So this is the distinction between the average value of a function given by a definite integral and an average in the sense of a mean of n numbers. But they're related. So let's look at the average value of a continuous function. So we're looking at the average value of the infinite output values from a continuous function. So if you think of the graph of a function and what the average value might mean, you would expect that half of the values would lie above this average or mean, and half of the values, in other words, half of the points, would lie below this average. So assuming that this blue line is the average value. So let's look at this particular example, this cubic function, on the interval -1 to 2. So what we're going to do to find the average, the continuous average for this continuous function is take values from this function. We're going to take more and more values, and we're going to let the number of values that we use to determine the mean go to infinity. So we're going to do the same type of process we did when we found the area under the curve and first define the definite integral. We're going to subdivide our interval into n subintervals, each of length delta x. And then we're going to pick a value from each subinterval and evaluate the function at those values. So what do we do when we find the average? We sum the values and then we divide by n. So we're going to be doing this for successively larger values of n. So for example, suppose n is 3. So we're taking 3 points from this function and we're going to evaluate it at those 3 values and sum them. So for an n is 3, we'll subdivide our interval into 3 subintervals, and you can take any point from each subinterval. So these x values mark, or these crosses on the x-axis mark the subintervals. So I'm taking the midpoint of each subinterval. You can actually take any point from these subintervals. I'm going to evaluate the function at each of those x values, sum them, divide by 3. And so my estimate is 0.79. So now suppose n is 4. Then delta x is 3 over 4. So I have 4 subintervals of length 3/4. And then I'm choosing the midpoints of each of those intervals. And again, I could choose any x value in those intervals, subintervals. Summing the values and dividing by 4, I get 0.77. So continuing on like this, we've seen enough of these examples where we let n get larger and larger and get a better and better estimate. So what we're going to do here is let n go to infinity. So this should look familiar. We're summing function values, but instead of multiplying by delta x, we're dividing by n. But we can get delta x back in the picture, so we can use an integral by replacing n with b minus a over delta x. So then I can factor out that 1 over b minus a, and that delta x is in the denominator of this fraction of this denominator. So that's equivalent to multiplying by delta x. And so that average calculation turns into this sum. So if we let n go to infinity, remember that the limit as n goes to infinity of the Riemann sum is the definite integral. So when we take that limit, we have this definite integral from a to b times 1 over b minus a, and this is just 1 over the length of the interval. So this is where our definite integral comes in. We just need to remember to divide it by the length of that interval b minus a. So now let's look at that function, this cubic function again, on the interval minus 1 to 2. So we had approximations of 0.79 and 0.77 when we looked at 3 and 4 function values. Now if we take the definite integral and use this function's the average value formula, I would get the definite integral from minus 1 to 2 of this function times 1 over 3, because 3 is the length of this interval. And that gives me 3/4, which obviously is 0.75. So let's look at another example. So to find the average value of 3 cosine x on the interval minus pi over 2 to pi over 2, I determine the length of my interval, just pi. Then the function average is 1 over pi times the definite integral from minus pi over 2 to pi over 2 of 3 cosine x. Finding that definite integral, I get 6 over pi. So that's the average value of this function on minus pi over 2 to pi over 2. Now when f is a positive function, that means that the entire graph is above the x-axis. So the average value of a function is really just giving you average height that the graph is reaching, is occurring. Here's another example of an application. So the velocity of blood flow in a blood vessel is different depending on where the blood is in the blood vessel. So, and it also depends on the length of the blood vessel and the viscosity of the blood. So the velocity of a blood vessel with radius capital R and length L at a distance little r from the central axis is given by this formula. So in other words, the blood vessel is capital R units in diameter, but the blood that's rushing through it is small r units from diameter away from its center. So to find the average velocity with respect to little r over this interval, we again would use our average velocity function formula, and it would be 1 over r, where capital R is the width of the interval, times the definite integral from 0 to capital R of our velocity function, and we're going to integrate with respect to small r. And we get this expression, p times capital R squared over 6 times NL, where N is the viscosity of the blood and L is the length of the blood vessel. And then we're asked to compare that to the maximum velocity of blood going through this blood vessel. And remember, that would have been, we would need to take the derivative of the velocity function with respect to r and find the critical value, which is just r equals 0. So in other words, the when the blood is flowing directly through the center of the blood vessel, it's flowing the fastest. And that occurs when r is 0. And this is the maximum velocity at that point. So this section was short and sweet. You just need to remember that the average value of a function f on a closed interval is just the definite integral of that function times 1 over the length of the interval.